Hello, Professor and TA. My name is Xinre Chen, and I will introduce my project. My project is optimization of the backpropagation network. It is optimization for serial code. Um, we will use CUDA to parallelize the serial code so that we can increase the program running speed. So actually, the project high-level idea is we go through the code, C code, and then find some place we can parallel. The main idea is we just go through some for loop because for loop is easy place we can do the parallelize. Yeah, so actually, I go through some for loop and find some for loop it doesn't have dependence on previous result, so that is a good place to parallelize. If we have dependent, we cannot parallelize the program. So actually, this propagate layer function, it will run a lot of times, and it doesn't have dependence on previous results. So I choose here to use CUDA to optimize it. Actually, I do a experiment and find this inner loop will run like 0.4 billion times, so it is a large time. So if we can optimize here, we can get a very large improvement. So we can see a code here. It has two loops, out loop and inner loop. So actually, the first idea coming to my mind is we can treat the out loop as a block, and then the inner loop as each thread in each block, because we just want the result of the out loop, so we can assign the result to each block when all the thread in this block finish their calculation. So that is the basic idea. Actually, here we can see we use we must sum some information to this sum. It's very similar to our histogram program. So we use a shared memory for the sum and use some atomic add API to add this result to the sum shared memory, and then assign that result to the output. Yeah, that is a high level idea and basic idea of how we parallelize the program. So actually here we can see the detailed implementation. Yeah, as I say, we use a shared sum and then add this result to sum. And here, PID is block ID and the TID is thread ID. We just actually we interpret this equation and change this two-dimension array to one dimension. Yeah, so actually here we can see J actually is TID, I is block ID, as I just explained the principle. So here, this code just interpret that equation, yeah, here. And then if we get the sum result, we can use this equation to to assign the result to our output. And this one is a block ID, as I say. So besides the kernel, we also need to malloc some or copy some data to our CUDA kernel. So actually, this is the information we need as the input, and this is the output. So actually, this one this one is very similar to our assignment. And how we design the block grid and the thread per block. Actually, it is easy because the out loop is block, so block size will be the iteration count of the out loop, which is upper units, and the inner loop will have these iterations. So the thread per block will be the inner loop count, which is this one. So that is our block grid thread per block. Yeah, after that, we must malloc some memory to this information. Actually, here is a very important place because we cannot malloc this information each time we call the propagation layer, because this operation is very expensive. So I malloc this one on the main function, and then we just init one time, and each time we call propagation layer, we assign the new data to this memory space. So in this case, we can improve the performance. So yeah, the evaluation of the result, actually the C code will run 7.3 seconds, and our CUDA will only have 4.3 seconds. So we have almost 14% performance improvement. So actually, the limitation of my code is actually we still copy data from CPU to GPU or GPU to CPU each time we call the propagation layer. So actually, we can groom the code in detail to find where the code will separate from CPU and GPU, and then we just optimize the whole GPU code, and then we do not need to copy data each time we call the propagation layer. I think in this way we can improve the performance more further or more. The challenge of the program actually is yeah, I firstly in the initial stage I malloc the memory each time we call the propagation layer. Yeah, as I just said, the result of the running speed is 37 seconds because we malloc the memory each time we call that function. We will call that function maybe 0.1 billion times of whatever it is a large count. So so I move the malloc outside that function and just malloc it in the main function for one time. So in this case, the running speed is 4 seconds. It's a very large improvement. Yeah. My team, I just have, I am alone in this project, so I do 100% of the feature implementation. Okay, that is a general idea and some details of my project. So, and then I will show a demo of my project. We first log into our server and go to my final project, and I enter this running instruction to the document. You can just copy and then to run the project. And then we compile firstly, and then just run the binary code. As we can see, the CUDA will take just 4.6 seconds. And we use the serial code. Actually, here is the original serial code. And let me Actually, I also improve the back propagation layer. They have the same methodology. So here we just use the original C serial program, and we compile it again and to see how long it will take. As we can see here, it costs 7.1 seconds. Yeah, it is a 40% performance improvement. And yeah, I think that's all on my side. Let me check whether these are high-level implementation progress result. Yeah, I think I covered all the instructions. Thank you, Professor and TA.